I feel that we are really fortunate today for this session. It's great to have Shafi as the original inventor for zero-knowledge proof to give the historical perspective. And now we have really world's leading researcher in cryptography, Dan Boneh from Stanford University, to talk about the really exciting recent development in ZKP as well. With that, thanks, Dan.
Excellent, thank you. All right, Shafi, this was wonderful. I have to say, before I get started, I have to say that Shafi's work had a lot of positive impact on my life. So thank you for all of your contributions. All right, so I only have 15 minutes, so I'm going to keep it fairly short and high level. And I wanted to talk a little bit about kind of the state of real-world proof systems and where we are. So yeah, so let's dive right in. So first of all, one of the things that's really quite remarkable that's happening these days in the world of cryptography is if you think back a couple of years back, really the main customer for cryptography was sort of the internet, right? It's basically everything that we were doing in cryptography was designed for internet-based applications. You know, how do you get your credit card securely to Amazon so nobody can steal or change or read it and so on? And that primarily has to do with secure communication, which is crypto mechanisms like encryption, key exchange, etc. Now, what's happened in the last couple of years, in the last decade basically, is that cryptography all of a sudden has a new customer, right? This new customer is the blockchain systems. And what's very interesting about this is, first of all, blockchain systems are very receptive to new ideas in cryptography, whereas on the internet, it's very, very difficult to deploy a new idea. Yeah, the internet is sort of ossified. It's very difficult to get new ideas adopted. The blockchain space, you know, this community is very, very, very receptive to new ideas. The other thing that's interesting is that the crypto that's used by blockchains is actually quite different from the traditional cryptography we're used to. It's more has to do with data integrity, right? We're not trying to hide anything by and large. We're not trying to hide information on the blockchain. It's available in the clear. It's more about integrity. So we use different types of mechanisms than we do on the internet. Primarily, we're interested in signatures, commitments, zero-knowledge proofs. These are all integrity-based mechanisms. So yeah, these are front and center. And so I want to kind of emphasize that blockchain crypto is in some sense fundamentally different from internet-based crypto. Okay, let's see if I can move. Okay, I'll skip this slide. Okay. So what I wanted to talk about today is basically SNARKs and kind of their real-world deployments. I guess before we get started, let me just give you my obligatory slide on what a SNARK is. This is just kind of the high-level layman overview of what a SNARK is. So a SNARK basically is a succinct proof that a certain statement is true. I underline succinct because that's kind of the point of a SNARK. And the classic example, the hello world of SNARKs is, prove that I know some message M such that the hash of M is equal to 0. Yeah, I know a hash pre-image. The point of a SNARK is I can give you a proof that I know such a message M in a way that's the proof is going to be very short, and it's also going to be very fast to verify. Yeah, that's what succinct means. It's short and fast to verify. Now, if you think about this for a minute, if the message is like a gigabyte long, right, my pre-image of 0 happens to be a gigabyte long, the trivial proof where I just send you the message over is not short, because it's a gigabyte long, and it's not easy to verify because the verifier has to rehash the entire message. It's really quite remarkable that I can give you like literally a 200-byte proof, right, that will convince you that I know a gigabyte message whose hash is 0. The proof is only 200 bytes, and you can verify it in just a few milliseconds. This kind of sounds impossible. It sounds mind-boggling that this is at all doable, but in fact, that's exactly what SNARKs let you do. Now, of course, so this is just a basic idea of a SNARK. A ZK SNARK adds another feature, which is that the proof itself reveals nothing about the actual message. Okay, so today we're actually seeing this enormous interest in commercial deployment of SNARKs, and I wrote just a few of the companies in this space. I guess the top row are people who are actually developing new proof systems. The second row are people who are using these proof systems, and the third row are a few of the companies who are building hardware accelerators for provers. There are many more companies in the third row. It's just they're not all public, and so I only put the name of the public ones. But this is a really hot space. Now, if you think about this for just 1 second, these are companies. These are not small companies. This is not like 1 or 2 person firms. Some of these companies on the list here are worth billions of dollars, and all they do is basically develop and deploy SNARK systems. How often do we get to say this? That something that literally a decade ago was considered pure theory all of a sudden is transformed into a huge industry worth billions of dollars with hundreds of people in each one of these companies only working on deploying these systems. This just doesn't happen. Yeah, I mean, hardly ever does this happen. And so this is like, I don't know, this is like, we should all stop for a minute and appreciate like how remarkable this thing is, that something that was like, came out of the world of theory all of a sudden has become an enabling block for an entire industry. And in fact, there is a very large industry devoted to it. So this is kind of a remarkable success, I would say, of theory and the theory of cryptography. Great. So the next question to ask is, well, why is this happening? Like, why is all this effort devoted to building these SNARK systems? And the answer, surprisingly, the answer comes from a paper that's really old. It's a paper from 30 years ago. Yeah, so let's look at this paper. This is one of the earliest papers on what's called computation outsourcing. The title of the paper is Checking Computations in Polylogarithmic Time. How do you check that a computation was done correctly? It was written by Babai, Fortno, Levin, and Szegedy. It's a very famous BFLS paper back in 1991. And if you read the paper, one of the statements in the introduction says, in this setup, a single reliable PC can monitor the operation of a herd of supercomputers working with unreliable software. That was the idea back 30 years ago. When you read this 30 years ago, this sounded like, oh, you know, you just wrote this as a way to kind of motivate your results. But of course, generating the proofs that were required for this would probably slow down the supercomputers too much. Really, what the authors meant to say is, if we translate this a little bit, is if we have like a very slow and expensive computer, that's our single reliable PC, a slow and expensive computer can verify the operation of a herd of GPUs that are working with unreliable software. That's what they meant. And for 30 years, basically, we were looking for what is a slow and expensive computer? Right? Our phones were getting faster, you know, our laptops were getting faster. So kind of the need for a slow and expensive computer, it wasn't really materialized until, well, finally today we have a slow and expensive computer. What is a slow and expensive computer? A layer 1 blockchain, right? So that's exactly, this sentence actually became very much reality, and that's actually what's driving a lot of this industry. I would say the takeaway message from this is when a theoretician tells you that something is important, even if today it seems like maybe this is science fiction, maybe they're just 30 years early, right? But when theoreticians tell you that something is important, you should take them seriously. Yeah, I would say that that's a very important takeaway message from this experience. This became literally, this sentence became a multi-billion industry that's now, as you can see, spanning many, many, many different companies. Great. So why is this possible now? Basically, you know, it did take 30 years of really kind of amazing ideas, really beautiful, beautiful ideas that make these SNARK provers fast enough so they run in linear or quasi-linear time to generate these proofs fast enough. I'm not going to go into the history of what happened over these 30 years. If you're interested in learning more, there's a very large bibliography, very good bibliography that I put a link to at the bottom there. You can kind of go and look at some of these papers, but really, it's really a really beautiful, amazing set of ideas that made this all possible. Great. So what now? So what's interesting is what's driving a lot of these developments, what's driving this industry is actually, again, the need for them in the blockchain space. Again, what's remarkable is these proof systems and these zero-knowledge proof systems. So proof systems is for outsourcing computation. The zero-knowledge property adds another feature, which is the zero-knowledge. They provide, it's not like, you know, it's not like there are other ways to do this. It's like for some of these applications, the only way to provide a solution is by using these efficient proof systems, these efficient SNARKs. And as a result, we're seeing a lot of pull from the industry. So the industry is sort of asking for SNARK solutions, whereas in many other cryptographic systems, advanced cryptographic systems, kind of the crypto community has to push this into the industry. Here, there literally are no other solutions. Kind of the only way to let's say, build an efficient bridge between two blockchains is by using zero-knowledge-like techniques. Yeah, and so we're seeing this massive pool from industry that's demanding these technologies. And again, this is why we're seeing such a massive investment. So blockchains are driving the development of SNARKs. And so I listed some of the applications, ZK rollup, ZK bridge, ZK credit scores, where I can compute your credit score without actually looking at all your private data, ZK taxes, where you can prove that you paid the right amount of taxes without actually revealing all your income and all your financial records. There is, ZK compliance, where you can prove that you're compliant with local laws without actually revealing anything about your transactions. Again, these are kind of incredible tools that can only be done using these ZK proof systems. One comment that I want to say about this is that the ZK rollup and ZK bridge applications, which I think this crowd is very familiar with, what's interesting, ZK rollup and ZK bridge actually don't use the zero knowledge property, right? They only use the fact that the proof, this is outsourcing computation, they use the fact that the proof is succinct and easy to verify. So we could call them proof-based rollups and proof-based bridges, but ZK rollup and ZK bridges sound a heck of a lot better. So we'll just keep on calling them that. Yeah, so that's kind of where we are. But what's amazing, though, is, this is why I say we're going to the moon. Remember the Apollo program? They were going to the moon, but there were all these residual technologies that came from building the Apollo program. And the same thing is happening here. There are lots and lots of non-blockchain applications to the SNARKs that are being developed. And so let me quickly walk you through one non-blockchain application that's kind of fun to describe. So this one is what I'll say using zero knowledge basically to fight disinformation. So as you know, there's a lot of disinformation out there on the web, lots of misleading images. They claim to be taken in one place, but actually they're taken from a different place. So much so that there are lots of sites out there that will try to educate the public on whether images are valid or whether they're correct or not correct. Basically there's lots and lots of, this is kind of a serious problem that the media industry is grappling with. Well, so let's see how zero knowledge can actually help with this problem. So it's kind of interesting that in fact the camera world is kind of very much aware of this, and so they came up with a standard. It's called the C2PA standard. It stands for what is it? Content, provenance, and authenticity. And what it is, well, it's a standard for content provenance. So what it is basically something that's built into the camera. And in fact, this summer Sony launched a camera that provides this ability, where the camera itself has a secret signing key embedded in the camera. We have to assume that this secret signing key is protected in the camera, so it's hard to extract the key for the key from the camera, but let's assume that's the case. Once you have such a camera, every time you take a picture, the camera, what it will do is that it will sign the raw image along with the location and the timestamp where the image was taken. So all the metadata is signed by the camera, and that's the C2PA signature that's now attached to the image. Okay, so these cameras will generate certified images that you know where they were taken and at what time. And of course, when this is shipped to the browser can now verify that if you're reading an article about a particular place in the world, you can verify that that image in the article was really taken at the claimed place and time. Okay, good. So what's the problem? This seems to be perfectly fine. Why do we need zero knowledge for this? Well, the problem is that this is not how the world works. Yeah, the problem is that when a newspaper takes an image from a camera, it doesn't just ship the image directly in the news article. What they'll do is they'll use some editing software to edit it. For example, they'll downsize it. Yeah, so images are, they have very high resolution. What newspapers will often do is they'll scale it down. And if you look at the New York Times, their images are 1,500 by 1,000. Even though cameras, of course, produce much, much higher resolution pictures, they do this to save bandwidth. They might crop the image, right? There might be things in the image they don't want, that are private, that they don't want the world to see, so they might crop it, they might grayscale it, and so on. The problem, of course, is once you do this, now the browser can no longer verify the signature, right? The signature was on the original data, and now, since you've edited the original image, the browser cannot verify the data. So what do we do? Well, the C2PA world had a solution, which I'll put in quotes, which was that as you choose your favorite editing program, let's say Photoshop. As you use Photoshop, Photoshop will basically sign the fact that the only thing you did is you cropped the image, for example. But of course, now you have to embed keys in software. You have to trust that the keys actually are, you have to trust the software. As we know, software is kind of, well, I don't need to say much. You understand that this is not a very, very reliable solution. So what do we do instead? What do we do instead? We use zero knowledge proofs, exactly. So the solution is basically, well, let's use these SNARKs, and this is, I should say, work with Trisha data. So let's use these SNARKs so that what we will actually embed in the newspaper article is the original photo with its metadata, sorry, the edited photo with its metadata, and a proof pi. Now, what does this proof do? This proof basically is a proof of knowledge that whoever created the proof knew the original image, the editing operations that were done to the original image, and the C2PA signature on the original image. And it proves these three facts. The signature is a valid signature on the original image. If you apply the set of operations to the original image, you get the photo that was actually sent to the browser, and the metadata of the photo sent to the browser is equal to the metadata of the original image, right? That's a succinct proof. It's only 200 or 400 bytes. Again, 200 or 400 bytes can be embedded in the image, and the browser can verify the signature, and now they're guaranteed the only thing that was done to the image is maybe you resized it, you cropped it, and maybe you made it grayscale. That's it. Yeah, so that's the only thing that gets proved, and this is all possible because of the SNARK, because SNARKs have gotten so big, so good, that we can actually generate SNARKs of this type. Now, again, if you think about this for 1 second, these original images, they're images taken from a modern camera. These are like 5 megabyte images, lots and lots of pixels, lots and lots of data, and we have to produce proofs on these very large images. Traditionally, this would be impossible for SNARKs, for provers to generate SNARK proofs on such a large amount of data, but because of all the work on improving provers, this is now actually possible. And so not only is it possible, when we implement this, it turns out, these proofs are actually quite fast on a very weak laptop. These proofs are actually quite fast to generate. All this is literally we took the algorithms from ImageMagick. ImageMagick is a photo editing software. We just took the algorithms from ImageMagick, implemented them in one of the zero knowledge frameworks, and we're able to kind of generate these proofs in a reasonable amount of time. So the New York Times would be running these proofs. Right, they'll be generating the proofs, embedding them in the images, and the browser will verify that the proofs are valid. Verifying that a proof is valid is nothing. That's like 2 milliseconds to verify the proof. That's it, right? So you can see how the fact that the blockchain is driving so much technology is helping in completely unrelated areas to the blockchain. So I don't know, I think this is kind of a cool story. And I do want to point to this paper by Neve and Tromer from 2016 that also talks about proofs of editing photos. It's called Photo Proof, really, really cool paper. Highly encourage you to read it. If you want a challenge, this is something we need help on. So if you guys want a challenge, everything I said so far applies to editing images. What about editing videos? Can we do proofs on video edits? Videos are way more data than images. Today, the provers basically take too long to generate these proofs, but maybe somebody here has enough hardware or has enough patience, and you can actually generate proofs like this for videos as well. That would be super, super awesome. So please, this is important, and I hope one of you can work on this. The last thing I want to talk about in 1 second is actually where things are going with proof systems. And so the one thing I want to point to is that it's very clear that in the very near future, we are going to end up with what we would call a market for zero-knowledge provers, right? So it's not going to be the case that every company is going to generate proofs for itself. What will happen is there are lots of people with GPUs out there, potentially people with ASICs that are going to be available and ready to generate proofs. And so a market will emerge that anyone with a GPU can be paid to generate these proofs. It's very interesting to design this market. This is actually not a simple problem to generate an efficient market here. But what will happen is basically, we need to generate a proof that a bunch of transactions are valid. You can imagine one prover will generate a proof that 2 transactions are valid. Another prover will generate a proof that other transactions are valid. A third prover will generate a proof that those 2 proofs are valid. And each one of those provers will actually be paid for the work that they did. Yeah, and again, I caution you because it's very clear that this market is coming. What's not clear is how to design it from an economic point of view, so it's not a winner-takes-all situation, but in fact, all the provers will equally benefit and will increase availability for these provers. Yeah, so again, something to think about. I think this is a good area for research. All right, so I'll stop here. This was fun to do, so thank you all, and happy to take any questions. Oh, yeah. Thanks.
For an amazing talk. So we have time for one question. Any questions?
Run the ZKP on GPUs, but GPU is not specially designed for ZKP. Do we need like the specialized or friendly to ZKP proof generation in the future? And how do you think of this area? Thank you.
Yeah, absolutely. I mean, so there's, like I said, there's companies now building hardware for accelerating proof generation. You know, probably if I give this talk a year from now, my list of hardware companies is probably going to cover the whole slide. Yeah, there's a lot of hardware companies. Again, it's a very exciting area for architects, and so greatly in demand, greatly needed, and I'm really looking forward to seeing the ASICs that come from this work. Yep, absolutely. Yeah.
One more question. So one last question. Give me time.
Okay, Professor Dan Boneh. My question about it's very eye-opening for you mentioning that there will be a marketplace for ZK proofs. I wonder what's your take on whether it is possible to create some like useful POW kind of consensus. Like there's a lot of people looking into how to make POW instead of like randomly generate hash can do something useful. And I think ZK proofs might be one of the application. What's your take on whether that is totally possible at all?
I mean, actually, that's a longer conversation. This marketplace is not going to be the same as a proof of work marketplace. It has to work differently, and maybe that's a conversation that we should take offline. But it's very clear that marketplace cannot be the same as, for example, the Bitcoin proof of work marketplace. It has to work differently. Yeah.
Yeah. Thank you.
Awesome. Thank you very much.
Thank you.